Okay, so hello everyone. Today I will be covering heavy light decomposition on a tree. I will explain the entire topic and also do two problems related to it. So, suppose you are given a tree of n vertices. Now, the problem is that we need to assign labels to each vertices, like a permutation from 1 to n to each vertex. So, like let A be a permutation and we assign the value ai to the ith vertex. And now suppose that we are given a path between vertices u and v. There are n vertices. Now we need to find the minimum number of, like we need to minimize the number of ranges such that we can cover all the vertices on the path from u to v in x ranges, where each range covers a consecutive set of values l to r. So basically I will give an example. So suppose we labeled a tree like this. I will label this 2 and this is 3. Now suppose that we need to cover the part between these two vertices, and now we can see that we can do it in two ranges, 1 comma 2 and 5 comma 5. Now it turns out that in a tree we can always cover a path with at most 2 log n ranges. So a path can be like of any length from 1 to n, and we it's an interesting fact is we can cover it using at most 2 log n ranges. So did everyone get this part? So suppose we are given a problem, we are given a tree, and we need to set. There are two types of one query and one update. So in an update, we need to set all the nodes on a path to value v, and the query is that we need to find the sum of all the values on the path. And suppose that n and q are 1e5, around that. Still, some people are joining. So suppose that we are and we have queries and updates of two types, u comma v comma x. We set the value of the ith vertex to x for all nodes I on the path from u to v. The second, the query is of the form that we are given two vertices u comma v, find sum of values of all nodes on the path from u to v. Does everyone understand the problem? Hello. Okay. So now I will show you a tree, and we will categorize vertices as two types, edges as two types, heavy and light. And I will show how it helps. So suppose a vertex has x children. We reorder the vertices according to the subtree size. So the first one we visit in the DFS is always the has the biggest subtree size, and the next one, the all the rest have the size at most of the size of that vertex. So after reordering the vertices, we get this. Now suppose we do a DFS order labeling of the tree. This will be 1, this will be 2. This is just an example: 3, 4, 5, 6, 7, 8, 9, 10, 11. In this, if we can notice that the first vertex we visit, the first child we visit from a node has size at least the sizes of the other children. Now, if you notice one thing, that if there's a node, let's say K, and let the children be A1, A2, AM, subtree size of AK, let AI, for I between 2 and M is less than half of subtree size of K by 2. This is because the subtree of A1 has size at least the subtree of A2 and so on. So obviously, like, this cannot have size more than half. If it has more than half, then A1 also has more than half, and that would be a contradiction. So did everyone get this part? Okay. The subtree size of the children other than the first child is at most half of the total subtree size. This is because that the subtree sizes are sorted in descending order. So if subtree size of say A2 is greater than half, then subtree size of A1 is also greater than half, and then we will get a contradiction as the total number of vertices will be more than subtree size of K. Well, not exactly same as centroid decomposition. So now we will label the nodes as edges as heavy and light. So the edge from the parent to the first child will be labeled as a heavy edge, and the other edges will be labeled as light edges. Let's color that yellow. So this is a light edge, this is a light edge, this is a light edge. So now if you notice, if we do a DFS order labeling of the tree, then if U V is a heavy edge, where U is parent of V, uh, then start time U equal to start time V minus 1. So basically they have consecutive labels. If you can notice this. Did everyone understand the definition of heavy and light edges? Hello? Am I audible? Okay. So now suppose we are given a path from U to its ancestor. Let's take it as A and not as U. And U to its ancestor B. Then it turns out that we can decompose the path from A to B. Like, all the vertices are labeled by the DFS order and then are not their original number. Then it turns out that we can find at most log n ranges. Wait, leave this. So it turns out that from a path from A to its ancestor B, we travel through at most log n light edges. Well, this is because that the subtree size of uh, a node is at most half of its parents if it's a light edge, and so the subtree size at least doubles when we go up a light edge, and it can double at most log n times as the subtree size is n. So there are at most log in light edges and rest are all heavy edges. Did everyone get this part? This is the main part. Like, if you have any doubts, you can ask. Hello. Okay, so now I will like, if you see the path from node 8 to node 1, then you notice that these two, this is a heavy edge, then a light edge. So you can get two consecutive ranges. One is 7 to 8 and one is 1 to 1. And now when we go back to a previous problem, our problem was that we need to set all the nodes on a path to value x and also query the sum of nodes on a path. Now we can maintain a segment tree on these values. So the ith value of the segment tree corresponds to the node with ith DFS order. And so since we have split the path from A to its ancestor in log n paths, so suppose that we have two nodes u and v and we need to do on the path between them, we can find the lowest common ancestor, let it be c, and we do the same for path from u to c and v to c. So like this is if we maintain a segment tree of the values and their sums in a range, then we can, this is just like range updates, and we need to set all the values on a range to value x, and we need to do it 2 log n times. And so for some we just need to find the sum instead of updating, and like this is a standard problem using a lazy segment tree. So did you all understand the problem solution, like how I split the part into 2 log n ranges, and how we can do this using a lazy segment tree? Okay, so a simpler problem for this will be that you are given an array 8, A1, A2, A3, and AN, and the updates are change AI to X for X in range L to R, and second is query sum of AI for I in LR. So in this problem, we are given a range and we need to like do updates of range set and range query. So like, does everyone know how to do it using a segment tree? Like this is one of the very standard problems. Okay, so now in the tree we are doing a similar thing. We are just doing it on paths instead of like a simple range. Like the array one can be similar to a line graph, where the graph is a line of n minus one consecutive edges. And now using our heavy light decomposition, where we if we go up to an ancestor, I showed that it travels through at most log n light edges. So if we remove the light edges and the all the remaining are form consecutive ranges, because of the this property listed in red here, we iterate over the heavy child first in the depth first search. So the start time of the heavy child is just 1 plus start time of the node. So we can get a consecutive ranges. For example, from 4 to 1, there are no light edges, and 1, 2, 3, 4 all occur. So it's a consecutive range. Okay, so can you tell what did you not get in the login part? I can explain it better. Okay, so how is it login? So suppose we go up a node and it's a light edge, then the node must have at least one heavy child. Every node has a heavy child, right? Except the leaves. So if you notice, the size of the heavy child is at least the size of the other children. So let this be A and let this be B. So size A is greater than size B and size A plus size B is less than equal to size K, where this is K. Sorry for my handwriting. I will just write it as S instead of size. SA plus SB is less than equal to SK since they are disjoint subtrees. And SA is greater than equal to SB. So SB is less than equal to SK by 2. So did you get that the so did you get the uh, that the subtree has at most half size if like it's a light edge. So this is a light edge. Then size of C is less than equal to size of A by 2. Did you get this part? Because there is another edge which has subtree size at least that. So did you get the half? Okay. So if you notice that this can be written as size A is greater than equal to 2 size C. So now if there's a node and we go up to its ancestor, let's say we go to the root node, and then if we go through a light edge, the subtree size of that node doubles. Because of this, the subtree size at least doubles. And subtree size is less than equal to n for all nodes, since there are n nodes. So if you notice that this array is like non-decreasing, the subtree sizes if we go up and up, and for light edges it doubles. So yeah, okay, so it's log n. So now since it's log n and the heavy children for have consecutive start times, since it's just plus one, the next node were visited in the DFS, we can get log n ranges and split a path into two log n ranges by just splitting it into two paths from U to LCA and LCA to V. So did you okay? So heavy and light thing. For heavy, the first child of a node is heavy, and we sort the nodes in descending order of subtree size. So the subtree size of first child is more or equal than subtree of size of second child, and so on. And light are the other children are light. So if this is a light edge, the lower node is light node and light child, and if this is a heavy edge, the lower node is a heavy node. So did you get okay? So did you understand the login paths and how we are doing it? Okay, so if everyone has understood, can I move to the next problem? Okay, so I will be discussing a problem for pillars. So this is the statement. I'm sending the link in the chat as well. So all of you can read the problem first. I will give you a few minutes. So in this problem, we are given n pillars, and we can consider them as vertices, basically. N pillars, and these pillars are connected by n minus 1 bridges, which have height of 10 to the power 9 above the sea level. And it is possible to travel between any pair of pillars using these bridges. So this means that the graph is a tree basically. And now they have added more edges, m minus n minus 1 more edges, so they are total m edges to increase the convenience of travel. And now the height of these is not 10 to the power 9 but less than that. It can be any value between 0 and 5 into 10 to the power 8. Now the inhabitants want their pillar to be bi-connected. The definition of bi-connected is different from the usual one. Here it means that the graph has no bridge edges. It should not have any bridges. So a bridge edge is an edge such that if you remove that edge, the graph will get disconnected. However, there's a sea level problem, and the sea level may rise in the future. And if the sea level crosses the level of a bridge or equal to it, then that bridge breaks down. So now we have to determine the maximum water level at which the pillars are still biconnected. So did you understand the problem? Okay, now, and there are more updates. There are queue updates, and in each update they add a bridge of any arbitrary height. And after each additional bridge is added, we have to report the maximum level at which all pillars are still biconnected. So basically, we are given a graph, and each vertex has a weight, which is the height of that bridge, and we need to find the minimum value, maximum value x, such that if we have maximum value x, such that if we have only the bridges with height more than x, the graph is still biconnected. Biconnected means no bridges. Now there are subtasks also in this problem. So there are a lot of points for q equal to 0, and which is not the main problem. The main problem is when we can update bridges and like add a lot of bridges. So first we will see how to solve q equal to 0, which means that there are n minus 1 initial bridges which form a spanning tree which have height at 10 to the power 9. These have height more than everything, and it's quite clear to see that the answer will be less than 10 to the power 9 always to have the graph biconnected. Now notice that if the answer is less than 10 to the power 9, these edges will remain and these will form a spanning tree. So now we have to ensure that none of these edges are bridges, and that will be actually be sufficient since it's a spanning tree. And so each node will be in a cycle. So suppose we there are additional bridge of the form u to v. So we add a edge of type 2 between u and v, and it has a weight. Now we need to find the maximum height at which all the edges in the original spanning tree are covered by an edge. Cover means that for an edge u to v, we mark all the edges on the path from u to v. So did everyone get this part? Okay. So now it turns out that for each edge, we can calculate the maximum weight of an edge which passes through it. Passes through means for an edge u to v, this edge lies on the path from u to v. So we have to find the maximum value of an edge. Now see, if you see u to v, if we can somehow do an operation of being able to set all the edges on the path from u to v. So suppose value of an edge. Oh, okay. Also, instead of marking the edges, we will just you mark the lower nodes. We will denote an edge by the lower, like the depth node with more depth in the tree. So all the nodes will be marked from 2 to n. The nodes are marked in order of starting time, by the way. We do that because we will use that later in HLD. HLD is not needed to solve the subtask for q equal to 0, since there are simpler offline ways, but I will just show you how to do it using HLD because we have to do updates also, and for updates HLD is a must. So the updates are, so now it's clear that the updates are of the form: given two nodes u and v, mark all the values of all the edges to max of the current value and the weight of this node, the height of the bridge basically. And also, instead of marking the edges as I have told, for an edge we only we denote it by the lower node. Since each node has a unique parent, each edge is mapped to a unique value except the root. So did everyone get the part how we reduce it to range maximums on a graph? Okay, so now we can consider an update. Suppose initially all nodes. Also, we have to see the case where the graph is never bi-connected. So if the graph is not bi-connected, we have need to output -1. So initially we have a spanning tree and we keep adding edges, u, v, not edges, but these are like updates. We have two nodes u and v, which denote an edge connecting u and v with weight c. And now we need to max the values of all the edges is 0 initially, and we need to maximize all the wait instead of 0 we will do it as -1, because if we need to print -1 when like the graph is not bi-connected, so we do a operation of the form for all edges between u and v, we max their value by c. So max previous comma c, new equal to max previous comma c. What part do you want me to repeat? Can you tell? Okay, so we are not doing any range update right now. I have not told it yet. We just need, this is just an operation. So if these are the two nodes u and v and we have the value 2, so since all the values are lesser than that, we can just change it to 2. Now suppose we have these two nodes and we need to maximize the value by 1, we just change these to 1. And notice we always maximize it and we don't like go to a lesser value. So did you get it now? Okay, this is what I explained. This is like, did you get the updates part? Like how the problem reduces to finding the minimum value such that okay, so for an edge to find the maximum value, we need to find the maximum value of an edge which connect which has this edge on the path between the vertices. So this way, when this edge is there and the n-1 edges are always there, this edge will not be a bridge. We need to ensure that all edges are not bridges. So, so what we do is we find the maximum value of each edge and we find the total minimum value of all the edges. Did you get this? Okay. And so now we will use our previous HLD algorithm. So previously we were setting the values of u comma v comma x to a value and then querying sum. So now what we need to do is for a path we need to maximize all the values to that value. Maximize it to that value and we just need to query the minimum of all the edges. So we can, if we can maintain a segment tree which maintains minimum of a range, we just need to maintain a minimum of a range. And suppose like this is in range L to R, we maintain the minimum value of an edge in that range. and then the answer is just the minimum value of everything. And also since the segment tree only needs to maximize it, so suppose we need to maximize the values of range L2R by X, we can just like update the minimum value. Like if the minimum value is more than X, we are done, and if it's less than that, we just change it to X. So did you all get this segment tree part? How are you be doing, maintain, like doing max operations on the segment tree to maintain the minimum? Okay, so now I will show my code for the heavy light decomposition. I think it's already open. So first, as I showed, we first calculate the subtree sizes of every node. So this is the DFS2 function which accomplishes that, and then we sort the values in descending order so that the biggest subtree goes first. Now what we do is we calculate the start times, depth, parent of all the nodes. This is for lowest common ancestor calculation and the HLD part. This is like very standard, so I don't think I need to explain. And now what we do in the smart thing we do is, for every node we maintain the highest node to which we can go using only heavy edges. So suppose a node has a parent, and if that is a light edge, the value of the node is that node only. But if it's not a light edge, the value of the node is the value of the parent of the node. So in our original tree, the value of 4 will be 1, the value of 3 will be 1, the value of 5 will be 5 only, since 3 comma 5 is a light edge. And now we are given updates. So I will have declared a function add, like AA and BB are like the no, endpoints of the vertices of the edges. And now this is a function which does our heavy light decomposition. This is a standard segment tree where we maintain the range minimums and we do maximums on range updates. So we set value of AI to max AI comma C for all I in a range. So did you all understand a bit of the code? So these are some tiny cases where we need to consider if A is a parent of B or B is a parent of A. In that case, there will be only one path. In other case, we decompose the update into two paths, such that each update is from a node to its ancestor. Now, in our code, suppose a node is A and we need to update from A to B. We need to maximize all the values. So from A, we go to its label. If its label is B or above it, we can just exit after doing the last operation. Since these form a consecutive range, a node and all its ancestor, which can be reached only using light, heavy edges, we can do range updates. And now after doing it, there's an if there's a light edge now, if there's a light edge, we can just do a point update of that. And now we set this as the current node. We go to its heavy parent and we do the update on this range, then another light range. So this way we can do at most 2 log n range operations, and using a segment tree we can get n log square, n plus q log square complexity. So did you all get that part? We are maximizing the values, and here the segment tree maintains minimum of a range, so we just output the first node. We have also declared all the values as -1, so that if the tree is not bi-connected, we can just output -1 as it is required in the problem. So did everyone understand the solution? Okay, I will send the link in the chat also if anyone needs to refer to it. I will now cover an interesting problem. which is spring cleaning from CUI 2020. So you all can read the problem. I will give you a few minutes for that.